Okay, so let's begin. Today we're actually going to start talking about chapter 2.
So Professor, the next quiz will be on Friday?
What?
The next quiz will be on Friday, right? Are you going to move since we are...
We don't have class this Friday. We don't have class until next Tuesday. And probably at that time I'll give a test, not a quiz. Should I give a test on Tuesday?
Take some everything or just that online?
Or maybe I'll give the test on Friday. I'm not sure.
We don't have class on Friday.
No, the next week.
There's still no class next week? Okay, so next Tuesday.
Another holiday.
So,
Where do you prefer?
what? Why not Tuesday?
Why not?
Okay, so Thursday, what's the date? It's October 2nd. Is that Thursday? I think.
Wait, give us a second.
It's October 2nd.
I'm not going to eat anything like that.
Okay, on topics in syllabus.
Oh, wait. No. Oh, man, that's my calendar. Where's that purple calendar? Does anybody have white eyes?
I already posted a few review problems, but I want to find more, so I'll make up some more to put there. Because actually on the final, what we've done so far doesn't show up that often, so there wasn't a lot of examples or whatever. I'll deal with that. So there are some problems on the website already, but I'm going to put more on it soon, maybe by tomorrow. So just be aware of that. So it's chapter 1 stuff. So limits, intermediate value theorem, and all the stuff that we've done up until 1.6. So now we're going to do chapter 2.
You're doing two sections at once?
Yeah. So in 2.1 they talk about the derivative at a point, and then in 2.2 they generalize this as a function that you can plug in any point. I don't really see the benefit in splitting it up, so I'll just talk about it all at once. Yes?
Did you say today was a review for the test?
Yeah, I think you
Yeah, you
did.
did say
Yeah.
that. That wasn't prepared.
What? Yeah, you the lecture.
I'm not mentally
No, I had a review. I had questions.
Yeah, you did say that.
Okay, well say it, well now the test's on Thursdays. Do the review on Tuesday.
This is gonna confuse us.
We'll be better prepared.
Oh, it's fine.
We'll be better.
Okay, so,
Good on the test.
thought experiment. First, background. Does everyone know what speed is?
Speed, yes. Meters per second.
Meters per second is an example of speed, sure. Like in general, what is it?
Miles per second. How fast?
Well, speed is the magnitude of velocity, sure. And velocity is like distance covered per unit time, right? So examples would be something like meters per second or miles per hour, etc. Right? You can also think of it as the rate of change of distance. Right? And the general rate just means you're looking at how something changes per time, so it coincides with this. I just want to make sure that we all know what this is. Right? So it's just measuring how your position or your distance from a certain point changes per unit time. And when you call that measurement, you say it's speed. Right? So a car moving at 80 miles per hour, you're just saying, okay, it's moving at a speed such that in a 1 hour period, if it maintains that speed, it will cover a distance of 80 miles, right? That's how we sort of measure speed. So suppose a particle travels at a constant after 1 minute. What if I ask you that question? So we know something's moving. I measure, after 1 minute, I measure how far it is from its original point. Do I want after 2 minutes? No. That wouldn't be a constant speed, actually. Okay. So after 2 minutes, it's 20 meters from where it starts. What is its speed? Sure. Answer. 10 meters per minute. Now, if you were to sort of want to graph this, how do you think you would do it? Like, how would you describe this in a graph?
Straight line.
It would be a straight line graph. What would you graph?
Meters and seconds.
Hmm?
Meters and seconds, the axis.
So here you put meters, right? So that's you're plotting your distance here. And here you put minutes, which is your time. And you can like plot it, right? So you know that after 1 minute you're at 10, right? So you have that point here. And then after 2 minutes, you're at 20. So you can plot that point here. And you could graph how it's moving by that picture, right? Now, if I ask you, how does 10 meters per second relate to this per minute? What would your answer be? It's actually the slope of the graph. Right? And so this is sort of where the idea of using a derivative to measure the speed of something using the slope of a tangent line, this is sort of where it comes from, right? So you sort of, if something's moving at a constant speed, it's easy to figure out what its speed is, especially if you're graphing it, right? But not everything moves at constant speed, but this is the starting point, right? So we figured, if we could graph something and it happens to be a straight line, we can figure out the speed, we can figure out its rate of change, right? But what if something is not moving at a straight line? What if it's not constant? What if its speed changes? Right? So that's the problem, that's called the rate problem. So we want to figure out, in the case of constant speed, it's easy to figure out, but what if you do not have this? What do you do then? Right? What if you have something like, that's how your thing is moving, right? And this is distance. And this is time. Right? So your speed is changing. You're speeding up and slowing down, and speeding up, right? Things are changing all the while. How do you measure that? Right? Now, it turns out there are two kinds of measurements that we are often concerned about. One is the average rate of change. And the second one is the instantaneous rate of change. Okay. Let's do these one by one. Let's see how we measure these things. Right? So average just means the speed over a given interval of time. That might not be a unit amount of time, right? For now, we use speed and velocity interchangeably. They're actually different, but we'll make it precise at some point later. So this is some change in distance over interval. So, for example, that's time and this is distance, and we know whatever this car is doing is here, or particle, car, plane, something. Now let's say I know after 1 hour it's at this point, and after 2 hours, or any amount of hours, it's at that point. Right? So for 1 hour it's at something like, let's say 10 miles. And at this point it's 50 miles. Right? So I want let me make it not 1. Okay. Now actually, what is the speed on average over this 3-hour window, right? Well, how would you do that? Right? You don't care about how it's increasing or decreasing in speed while it's going, but just on average over this long window, how do you think you'll measure the speed on average? Yes?
Just do 50 miles and 10 miles or 40 miles. And cover 40 miles within that 3-hour gap, so 40 over 30.
Right. And what is the connection between that? Well, that's exactly it. But you realize that if you actually connect these 2 points with a line, what you just described was the slope of that one. Right? So average speed in this case would be equal to 50 minus 10 over 4 minus 1. And this is in miles per hour. Right? So that's just 40 over 3 miles per hour. Right? And of course we can generalize this idea. So we have this random function that's plotting the distance of some object per unit time. I know at a point time equals a and time equals b. F of x equals distance of the object. What was the question? So we're sort of building on the idea of how we're going to figure out these 2 different kinds of speeds. So this guy would be f of a, this guy would be f of b, and so you just follow this idea of slope, right? So this, in this case, average rate of on the interval AB is just equal to f of B minus f of A over B minus A. Okay. Now I'm going to show you some alternate ways you could describe this. Sometimes we have, call this point X, call that point A. I'm just renaming things, I'm not doing anything crazy. Just showing you all the different ways you might see the formula. In this case, the average is f of x minus f of a over x minus a. Right? That should be something we've seen before. I put that on a few quizzes about. We could also set up the chart a different way. Call this point x. And then instead what I'm going to do is I'm going to use a second variable to measure the distance in time. Call it h. So this point will be x plus h. Right? Just saying that a time gap of h has passed, which means this would be f of x plus h. Right? And so in this case, your average rate of change is just f of x plus h minus f of x over, and this would be x plus h minus x. Right? So this would be f of x plus h minus f of x over h. Right? Should be looking familiar, right? That's been on pretty much every quiz I've given this semester so far. And you've been given this in pre-calc, they ask you to do this guy, and you're like, why? What? It's actually the slope between these 2 points, right? If I connect these 2 points here, draw a straight line connecting them, and do y2 minus y1 over x2 minus x1. They're all the slope, I'm renaming these, right? I'm calling them different things. So in the first case, I call this a and b, then I call it x and a, but I can also call it x and x plus h, right? But it's all the same slope. It's all y2 minus y1 over x2 minus x1, right? But these are some of the different forms you'll see. So they're all the same thing, so don't get confused. That's why I'm showing you all of them. So you can see any one of these, they all mean the same thing. You're just measuring the average rate of change over some period, right? And that guy should look familiar to you by now, right? The whole time we're asking about this guy since algebra and pre-calc, we're really telling you about average rate of change, but we just never mentioned it. So yeah, on average, that's how you would change. This is actually measuring the speed on average. Now here's the problem. How do you actually measure the second guy? Instantaneous. Instantaneous rate of change. In that case, what I mean, I don't mean the speed on average over some large interval. I mean at this instant, right? If I would freeze time right now, what speed is this object moving at, right? So here's this random curve that's describing, distance versus time. But now I pick literally a single point, x. What is the speed here? Right? Don't give me an interval at this instant. How fast is it moving right now? Right? Now you might notice a problem, right? Because we've been talking about speed in terms of the slope of a straight line. And to figure out the slope of a straight line, as far as we know, we need 2 points, right? To do that y2 minus y1 over x2 minus x1. How do you measure the speed now with 1 point? Yeah?
Tangent line.
Tangent line, right? It's exactly that's what we want. The tangent line is going to be the guy we want, right? Answer, find the tangent line. The tangent line is going to be describing how the curve is moving at this point, and if we measure its slope, we should be able to get the speed. So now the question is, how do we get the tangent line? So okay, we know we measure speed with a straight line. On average, that's no problem because we have 2 points to consider, but what if we only have a single point? How do we get that measurement? The answer is we need a tangent line. How do we get the tangent line? And the answer to that, not very rhetorical, limits is how we're going to do it. So it turns out at the end of the day, the answer to the rate problem is limits. The answer to the error problem is also limits, but that's for another time. So here's how we're going to do it. We know how to do some with 2 points, so let's start there. Oh, by the way, I should mention that this line is often called a secant line. So if you see that mentioned, this is what they're talking about. That straight line that measures the average rate of change, that's called a secant line. And if you want to measure the instantaneous rate of change, we measure that using a tangent line. Okay, so we start with 2 points because we actually know how to deal with it in that case. And let me just use the formulation with x and x plus h. So I start with 2 points and the line connected to 2 points. So now here's the idea that we're going to apply to move the 2 points closer together. Right? So here is our point, this is the x, this is the x plus h, right? So at this point they're here and that's your secant line. But if I move this point a little closer, then that would be the secant line. Move it a little closer, that would be the secant line. Move it a little closer, that's the secant line. Eventually if I move these points so close together that they're right beside each other, drawing the line between 2 points is sort of like drawing a line between 1 point. That's what we're after, right? Now what are we doing with this? We're sort of making the secant lines get close to the tangent line. Get close. Do we have a mechanism of how we measure when things get close, what happened? The limit is how we do this, right? So we're going to measure the slope of the function. Obviously, it's going to be that function I just put over there. And see what it does when our 2 x values get close to each other. So that's what we're going to do. So the idea is in our general graph here. Now this picture is just arbitrary. It can be anything. 2 points close? Well, I close the distance between them, right? Since h is the distance between the 2 points, we can just let h get close to 0 and look at what happens to our function. And this is equivalent to just taking a limit of secant lines until they approach a tangent line. So can you have a formula for the slope of a tangent line to a random curve f of x? This is simply going to be the limit as my h gets close to 0. Let the distance between these 2 points become nothing. So I can draw a line between them. F of x plus h minus f of x all over h. Which is again something we've seen before. Right? I actually asked you guys to do this a couple times. That actually gives you the slope of a tangent line. Right? So we knew how to find the slope of a secant line. That was easy. We had 2 points. How do you get the tangent line? Just push the points close together. How do you get things close together? Limits. Right? This slope is called the derivative. I'm not sure why they call it a derivative, but that's what it's called. I never looked into the history of the name, but that's what they call it, the derivative. At this point, I feel I should mention this, it's very important. You see the word derivative? You can think of it as being the same as slope. Which you can think of the same as rate of change. Or speed. Right? The concrete mathematical definition of these words is the derivative, which is this one. Yes?
Yeah, I'm sorry, I didn't get part where you said h equivalent to 0.
I never said equivalent, approaches. This is an arrow. Right, I just mean h
So
approaches.
where is that point in the graph?
H is not a point, h is the distance between the 2 x values. Right, so I want these points to be right beside each other. So all I have to do is close the distance between them.
Oh,
Right? By closing, letting h approach 0, this point will keep moving closer to that one by making h go to 0. That's what I'm doing. Look at the distance between my time interval, but I want that to be nothing. I want it to be the instant.
so in that instant you get
So that is called the derivative. It actually gives us the slope of a tangent line, which, if we find that slope, it's the same as finding the speed at an instant. Yes?
So for example, we're going to find the slope at h equals to 2, so we put 2 over there, right? H
No, the x value is the guy you care about.
As h approaches 2.
No, it'll always be h approaches 0.
So,
Yes, it'll always be this. I'm going to do some examples where I actually find it. I'm going to do some examples of when we actually find it, but this is what it is. Let's talk about some notations, by the way. For a function its derivative one notation I'm going to use all the time is the prime notation. This was the notation developed by Newton. F prime of x. Right? This is red. And it's a function, it doesn't mean multiplication, it's just like f of x. You put that in brackets to me. This is the input value. F prime is the function that tells you the slope at that input value. So here's my random function f of x. Here's a point x. F prime of x equals the slope of the tangent at this point. This is called Leibniz notation. Leibniz came up with this notation. Sometimes it's written as d dx of y or d dx of f of x. You won't see this often at this level, but sometimes we call it big D f of x or big D little x f of x. These all mean the same thing, right? Mostly we're going to be using this notation and this notation. This is the Newton notation and the Leibniz notation, but they mean the same thing. And we're going to talk more about this because this notation is actually pretty useful in general. Maybe let's do one example. I guess we can start with something simple. Okay, so I have the graph y equals x squared, which is that high. And pick the point x equals 2. At that point, if I drew a tangent line, what would its slope be? Right? That's the goal. I want to figure that out. So remember, this is just notation for the slope, right? The derivative, right? Exactly, the derivative at this point. And now we're going to use that definition. And this is something I've asked you on a quiz before, right? If your function is this, what is that limit, right? I've asked you this on a couple of quizzes before. So what we're going to do is we're going to find f of x plus h and plug that in here. What is f of x plus h for this function? Right, so x plus h all squared, right? Minus, and we're going to expand that somewhat. The original, which is x squared over h, and then we're going to start to find this limit, right? The limit we want to plug in 0, but we can't because h is in the denominator, so we have to simplify. This would be x squared plus 2xh plus h squared minus x squared. These two x squares die. I'd be able to factor out an h. That is gone. And so now, what will the answer be? Now I can let h equal 0. I get 2x. Right?
What if it's plus h?
Come again?
What if it's plus h?
H goes to 0, right? At this point, there's no h in the denominator. I can plug in 0, so I just do it, right? And 2x. Now, what's the significance of that function? It tells you the slope at any point of x for the function x squared, right? So, v point x. So, if I want to know what is the slope at x equals 2, plug in 2 into this function. Right? Turns out the slope of that tangent line is going to be 4 at the point x equals 2. What if I want to go further? Follow up. What is the equation of the tangent line at that point? How do I do that? Huh? Well, I know the slope already. So what do I need?
You probably need the y.
So x and y.
Just a single point, right? We can use a single point, right? So here's my function. This point, there's a line. I know the slope is 4. How do I find the equation of the line? Just pick that point. What point would this be?
That's x equals 2 and y equals 4.
2 comma 4, right? How do I get the 4? Just plug in the 2 into the original function, x squared. So,
We can just write y minus y1.
right. Y minus y1 equals n
Times
x minus x1, where n here represents the slope, but in general, we know that that's just the derivative.
y minus
Y minus 4, because that's the y value, equals n, which is also 4, x minus 2. So this is y equals 4x minus 8 plus 4.
plus 2.
What?
Oh, no. Yeah.
Yes. That's the equation of the tangent line at that point. Now we're going to do many more examples like this, but we'll stop there for now. This is sort of the introduction to how we find a derivative in this for a particular function.
So our
Not yet. No more time. For now, focus on the test. Ready for the test. Look at the review problem. Start.